But hey, this is a little hard to imagine with these drawings, so let's use models to demonstrate this, okay? Okay, so I've built two compounds here that are mirror images of each other. Check this out. These two compounds are exact reflections of one another. If you imagine a plane going down the center right here between these two compounds would be oriented in exact opposite orientations of each other across this plane, so that they'd be reflections of one another. So as you can see, here's a red reflected by another red, here's a green reflected by another green, a blue reflected by another blue, and a white and another white. But hey, we said that anything can have a reflection, so the real question is, are these mirror images non-superimposable on one another? And I told you that chiral compounds, compounds with 4 different substituents, have mirror images that are non-superimposable. So let me ask you, in these two compounds, are these black carbons in the center of these compounds surrounded by 4 different substituents? And okay, if you pretend that each color stands for a different substituent, then yes, these two compounds have 4 different substituents. Red, green, blue, and white, and the same thing on the other compound. So that would mean that these two mirror images are going to be non-superimposable on top of one another. But don't take my word for it, let's try this out. Let's try to place these two models on top of one another so that their atoms are aligned in the exact same orientation. Okay, so let's just try a bunch of different combinations here. And I'm going to start off by saying, okay, here's a blue and here's a blue. Let's just take those two blues and superimpose them, put them on top of one another. Okay, so this blue is superimposed on top of this blue, they're aligned. And sweet, we also see that a white is on top of another white. We've just superimposed 2 of the 4 substituents. But as we get to the other side of the compound, so let me turn this thing around for you. As we get to the other side of the compound, we see that a green is on top of a red and a red is now on top of a green. These guys don't match up, they don't superimpose. So we were able to superimpose 2 substituents, the blue and the white, but the other 2 didn't match up, the green and the red. So we'd say that overall, these were not superimposable. But don't get discouraged though. Let's try this one more time. Okay, and this time it's like, alright, since those red and green substituents were the problems last time, let's try to align those first and see what happens. Okay, so I'm just going to take the red of one compound and place it on top of a red of another. So let me invert it like that and turn it around for you like this. And sweet, these reds are superimposed, and hey, we also see that the greens are superimposed as well. But as we go to the blue and white substituents on the other side of the compound, we run into the same problem as last time. We were able to superimpose 2 of the substituents, the red and the green, but hey, these other 2 don't match up this time, the blue and the white. And no matter how many times you try to manipulate this, there will be no combination you come up with that allows you to superimpose all the atoms of these 2 compounds. Therefore, we say that these 2 compounds are non-superimposable mirror images. They are enantiomers, and it's because they have a carbon with 4 unique substituents, a chiral carbon. If these 2 compounds were achiral, if they didn't have 4 unique substituents, then you can superimpose these 2 compounds no problem. So for example, if I were to swap out these 2 greens and put whites on here instead, we would see that these 2 compounds don't have 4 unique substituents anymore. Let me show you. Okay, so what I've done here is I've taken the green substituents that used to go here, and I've replaced them with these white substituents. So hey, these carbons in the center that used to have 4 unique substituents on them now only have 3 different substituents, red, white, and blue. And hey, these compounds both still have 4 substituents, but now 2 of them are the same, white and white, giving them only 3 unique, 3 different substituents. And hey, if you don't have 4 different substituents, you're not chiral anymore, and you won't have an enantiomer. You won't have a non-superimposable mirror image. You'll still have a mirror image, which we see here, but it won't be non-superimposable anymore. Okay? So hey, if we look at these 2 compounds are mirror images of each other. But the question is, are they superimposable? So hey, let's try putting these atoms on top of one another and see if we can get all of them to line up. Okay? So I'm just going to start out by trying to match up these 2 reds. So let me go ahead and turn this like this and match up these reds. And if I do this, these reds line up, and hey, these whites also line up. But as we look at the blue and the white substituents, these don't line up. And you guys, did I lie to you? Are these actually non-superimposable? And no, you guys, I didn't lie to you. It may look like they aren't superimposable like this, but if you rotate this a little bit differently, like this, then you should be able to see that these two compounds align perfectly. They are superimposable. Blue on top of blue, white on white, and red on red. Anytime you have less than 4 different substituents, you're not chiral and you don't have an enantiomer. So go home tonight and definitely play with your model set, you guys. Test out whether mirror images are superimposable when they have 4 different substituents, and compare that to when they have 3 different substituents, 2, or 1, and see what happens. You should see that it's only when you have 4 different substituents that the mirror image will be non-superimposable. And these non-superimposable mirror images are called enantiomers. Okay, so let me go ahead and tell you guys one more thing while I have these models out. Okay, and I went ahead and resubstituted the green substituents on here so that we would have chiral compounds once again, compounds with 4 different substituents on a central carbon. Okay, so these two compounds are stereoisomers of each other because they have the same connectivity, same atoms, but different arrangement in space. For example, this compound goes from red to white to blue in a clockwise formation. This compound, on the other hand, goes from red to white to blue in a counterclockwise formation. So these compounds' atoms have different arrangements in space, and we call them enantiomers because they have the exact opposite orientations in space. One is clockwise, the other is counterclockwise, and this causes them to be non-superimposable mirror images of one another, okay? And cool, you guys, now that you know what enantiomers are, let me go ahead and tell you why we even study these types of compounds. Because really, if you look at these two compounds, they look pretty much identical, don't they? They look pretty similar to me, okay? The only difference is that their atoms are arranged in opposite orientations. One is in the clockwise formation and the other is in a counterclockwise formation. And you have no idea how to determine this just yet, but you will a little later. For now, let me just tell you that this is the clockwise enantiomer and this is the counterclockwise enantiomer, okay? But so what? Do their clockwise and counterclockwise formations make them that much different from one another? And oh my gosh, you guys, yes it does. And let me just give you a little background on this story to illustrate how important it is to recognize the difference between two enantiomers, okay? So check this out. In the early beginnings of organic chemistry, there was no such thing as a stereoisomer, as enantiomers. If you took OChem back in like 1900, the only isomers you would have studied would have been constitutional and conformational isomers. There was no such thing as stereoisomers because we didn't think there was a difference between the two compounds. In terms of their atoms, their connectivity, their melting points, they looked identical. We didn't think that the orientation of their atoms in space, be it clockwise or counterclockwise, made these compounds any different from one another. And when I say different, I mean behave differently in chemical reactions. But oh my gosh, you guys, people in Europe learned this lesson the hard way with something called thalidomide. Thalidomide was a morning sickness drug that pregnant women took to prevent from being nauseous. And let me just tell you that thalidomide was a chiral compound. It contained a carbon with 4 different substituents, meaning that yes, it would have a non-superimposable mirror image, an enantiomer. So when they were making these drugs, they were making both of the enantiomers, the clockwise and the counterclockwise enantiomer, because they didn't think that there was a difference. They didn't even call them enantiomers back then. They treated them as the same compound. But check out what happened, because after a year or so, these pregnant women had their babies, and like 1 out of every 2 women who took thalidomide had babies with horrible birth defects. Babies were coming out with like 3 arms, 16 toes, 1 ear, a half of a leg. Horrible, horrible birth defects. And nobody could figure out why, until they eventually correlated this rise in birth defects with the time that thalidomide hit the market. And they were like, oh my gosh, I guess there is a difference between clockwise and counterclockwise enantiomers. Because women who took one of the enantiomers was fine, it cured their morning sickness and they had normal, healthy babies. But women who took the other enantiomer had horrible birth deformed babies. And so if you ever go to Europe, you can still probably see the effects of this horrible mistake. because hundreds of thousands of babies were born with these defects and they're all grown up now. So thank God for the FDA, you guys. They never let thalidomide come to the United States. And that's why you've probably never heard of this drug and the horrible effects it's had. But trust me, ask someone from Europe and they'll know exactly what you're talking about because it was such a tragedy over there. And so hopefully now you understand why it's so important to tell the difference between two stereoisomers, between these two enantiomers. Because different enantiomers can have different effects in our body. And you want to make sure that if you're taking a drug, you're taking the correct enantiomer.